So yesterday we worked on position versus time graphs, okay? And a position versus time graph shows us where an object is at various points in time. Today we're going to look at velocity versus time graphs, which tell us how fast and in what direction an object is moving at any given time. Okay? So they could be showing us the exact same trip. Could be showing us exactly the same data. Would they look the same? They will not. Okay? So right now on the screen we've got a position versus time graph here on the left. Okay? From what we learned yesterday, what is this graph showing us? This position versus time graph. Right? It's showing us how much the position changes. What kind of motion is going on?
Forwards and backwards.
In this one?
Oh, a constant rate.
Right, a constant,
Rate of movement.
what do we call that? Starts with B. Constant velocity, right? This is showing us something moving at a constant velocity because the position changes by the same amount every second. Right? So remember yesterday I said if I asked you that, what I'd be looking for that shape would be the object is moving forwards at a constant velocity. Okay. What is that graph beside it showing us? This is a graph of an object moving at a constant velocity. This is a velocity versus time graph. What is it showing us? No, it's moving. But this graph is showing us the object's velocity. What's the object's velocity?
It's time or it's speed.
I'm actually asking for a number. What's the object's velocity according to this graph?
250.
Yeah, it's actually just a little bit above 250, about 260. Okay? Is the velocity changing? No, staying at 260. Are these two graphs showing the same thing? They are. This graph is showing us an object traveling at a constant velocity. So is this graph. They look a lot different though, don't they? It's because they're showing us the same trip from different points of view. One from the point of view of where is the object, and the other from the point of view of how fast is it going. Okay? Just looking at the same trip, but looking at it through a different lens. All right? Now, we can prove mathematically that these two graphs are actually showing exactly the same object. Right? And here's how we would do that. If I have a position versus time graph, and it's a single linear function like this one is, okay, what does the slope of the graph represent? Okay, we've gone over this for 2 consecutive days. Okay, this is something we need to know by now. Right? If I solve for slope, y minus b over x, what's on the y-axis? Position. What's on the x-axis? Time. So when I do this, that's final position minus initial position over, what does that calculate? How many people reviewed this stuff over the last 2 days? It shows. How much review should you do every night? Yeah, 10 to 15 minutes. Okay? Guys, if we don't review this stuff and practice it regularly, it's going to snowball fast. Okay? Physics moves really fast. And we've got to be ready for it. Okay, so if I calculate the slope of this line, what I'm doing is calculating the change in position, displacement, and dividing it by the change in time. All right, that ringing a bell now. Okay, so if I'm looking at this graph, this is B right here, so it's 100, okay? Y would be 1400, okay? And time would be 5 seconds. So if I do this calculation right here, I'm going to have 1400 minus 100, okay, because B was 100 and Y was 1400, divided by 5 seconds. That's 260 meters per second. Is that exactly what this graph is showing? It is showing an object moving at 260 meters per second for 5 seconds. Okay? All right, so we have to be able to do that interpretation. Okay, that's what we were working on yesterday, was looking at a graph and being able to figure out what is this graph showing me. That's exactly what we just did there. We looked at that position versus time graph, and we saw that the position was changing at a constant rate, meaning we're moving at a constant velocity, okay? And this velocity versus time graph is showing that the velocity is not changing. In other words, it's constant. Is that ringing a bell? Okay. Could I, from this graph, calculate the displacement of that object? Okay, how would I do it? Oh, that would be for this graph. I can't do that with this graph.
Velocity times time.
Exactly. Okay. Velocity equals displacement divided by time. This is an object traveling at a constant velocity, agreed? Okay. Do I know what that velocity is from the graph? I can read it right off of here. It's 260. And it happens for 5 seconds. So all I have to do is manipulate this formula. Okay, and I would have my 260 times 5, which, oh my gosh, comes out to the same thing it came out to here. 1300. Is that an accident, or is it a fluke, or is that like on purpose? It's on purpose. They're showing the same motion. I better get the same number. Okay, we're talking about the same object. It had better come out to the same thing. All right, when I did this calculation, I took what's on the bottom of this graph and I multiplied it by what's on the side of this graph. Agreed? Okay, did I essentially then just calculate the area of that rectangle? Base times height. Yeah? That little trick can help you calculate the displacement of an object from a velocity versus time graph, regardless of its shape. As long as you know your basic geometry, like rectangles are base times height and triangles are base times height over 2, okay, then you can calculate the displacement of an object from a velocity versus time graph. Because when you do this, you are actually just, if I calculate the area of any shape, I'm taking the average velocity for that shape and multiplying it by the time. Okay, so it always works. Even if it's not a rectangle. So, let's say it wasn't a rectangle. Let's say it looked like that instead. What is that graph showing now? Okay, sorry, I mean, what kind of motion is it showing? It's showing something whose velocity is not constant. What's happening to the velocity? It's increasing, and somebody said? It's accelerating, same thing, okay? So anytime there's a change in velocity, an object is accelerating. In physics, we don't use the term decelerate, okay? Acceleration is any change in velocity. If it's positive, then it's a positive acceleration, it's speeding up. If it's negative, it's slowing down or accelerating backwards, okay? So, in this case, this is showing an object that is accelerating. Okay? Now, could I calculate the slope of that line? Yeah, For sure I could. Okay, it's one linear function, so this formula still applies. Okay, am I going to be calculating the same thing that slope represented on this graph? No, on this graph, when I calculated the slope, okay, it was final position minus initial position over time. On this graph, when I calculate the slope, okay, y is going to be not a position, but a what's on the y-axis here? Velocity. Okay, so it's still going to be final and initial, but now it's final velocity and initial velocity, and it's going to be divided by time. Okay, this formula calculates acceleration. We haven't gone over acceleration yet, but we're going to come back to that formula a lot once we do. Okay, so the slope of a graph is the rate of change of y divided by x. Every graph, their slope represents something different. It calculates something different, right? On a position versus time graph, it's the rate of change of position, velocity. On a velocity versus time graph, it's the rate of change of velocity, or acceleration. Okay, so every graph, the slope represents something different. Okay, and you can figure out what it represents by simply plugging in what's y and what's x. And be able to figure out what it is. Okay? Everybody follow me there? Okay. Could I figure out the total displacement of this object? Yep. Okay, how do I calculate the area of a triangle? Base times height divided by 2. All right, so for this one here, that's going to be 5 seconds. Okay, times the height, which is 300, because it goes from 100 to 400, okay, over 2. Okay. Because it starts at 100, it doesn't start at 0. Right, 400 minus 100. Okay, so if I do that, 5 times 150 is 750 meters, I think. Okay, so that thing would go 750 meters while it was accelerating. Okay, I didn't change at all what I was doing before. This is still taking average velocity and multiplying by time. That's my average velocity. Okay, if my velocity increases from 100 to 400 at a constant rate, is my average velocity exactly halfway in between? Yes. That's why I can take the height of the triangle and divide it by 2 and get the average velocity. Okay. All right, what if instead of that, I had a graph that looked like this? Could I still calculate the displacement even though it doesn't start down here? Okay. How many shapes will there be? 2. Yeah. Could be a triangle and a rectangle. Now, if I got an equation for this graph, which I would have got, so y, and we'll just say m times x plus b, okay? This point right here is b. Would I know that value? Right? Google Sheets spits that out. Let's just say that Google Sheets spit out this equation here. 1.5x plus 3.7. How tall is this rectangle? 3.7, exactly, because this is b. Okay, and then if I knew what y was here at the top, I could go, all right, I can calculate the area of the triangle, I can calculate the area of the rectangle, and I can add them together. Okay? The reason we would want to do that is because this object is accelerating. That means it's going faster and faster. So this rectangle represents how far it would have gone if it didn't accelerate. and then I'll add on how far it went because it accelerated. And now I get its total displacement. Okay, so there's a lot of analysis that's got to go on. We spend a bit of time on graphs because I get that it's not something that necessarily clicks right away. Okay, but we have to get the hang of being able to look at a graph and go, okay, what is this graph showing? What's on the y-axis? What's on the x-axis? What does that mean? Okay, and it takes a bit of practice and experience to be able to figure that out. Okay. All right. This is a graph of a person running. It's a velocity versus time graph. What is the person doing here? They're what? Okay, they're accelerating at a constant rate. It's not possible to accelerate at a constant velocity because the definition of acceleration is to change your velocity. But people say that all the time, so I'm not singling you out. I'm just pointing out that I hear that a lot. I'm accelerating at a constant velocity. How? How are you doing that? That's not possible. It's just because we don't know we don't always understand the definition of acceleration is change in velocity. But we can say it's accelerating at a constant rate, and that would be true. Okay, so right here, yeah, they're accelerating. Okay, what are they doing here? Staying at a constant velocity. It's stopping on a position time graph. See, and that's the thing, right? We got to be able to shift gears between a position versus time graph and a velocity versus time graph. If I had a flat line on a position time graph, the position's not changing, the object is stopped. On a velocity versus time graph, a flat line means the velocity's not changing. But that means they're going at a constant velocity. Okay? What are they doing here? They're accelerating negatively, slowing down, I'd even accept. In fact, they're coming to a, okay, how do I know they're stopping? Well, not just that, it's not so much that it goes flat. What value does it get to? 0. Yeah. Okay. Okay, well this is exactly what would happen if you were running a sprint. Okay, you would, the gun would go off and you would accelerate. You'd run as hard as you can, but there comes a point where you keep pulling as hard as you can, but you can't run any faster. You reach your top speed. Okay, and you hold that top speed until you get to the finish line, and then you stop. Okay, that's exactly what that graph would look like. Now, this person's not particularly fast. Okay, 8 meters per second is actually not very fast. To give you an idea, Usain Bolt's maximum speed is over 17 meters per second.
So it's like walking speed.
What's that?
It's walking speed.
17?
No.
Oh, 8. Well, I mean, 8 meters per second is, I mean, you're running, but you're not sprinting. Well, I mean, if it was me, because I'm old, it would be sprinting as hard as I could. My knees flying apart at the seams and stuff like that. But yeah, for an Olympic athlete, that's I'm out for a jog kind of thing. Okay, but yeah, 17 meters per second. Now, just to give you an idea, this room is maybe 15 meters wide. Can you imagine somebody going fast enough that they travel the entire length of this classroom in 1 second? Okay. Actually, I don't even think I think it's like 10 meters wide. So this would be like this room, the hallway, and partway into the chem lab. 1 second. Now, he doesn't run that speed the whole race, obviously, for the 100 meters, okay, because he's got to accelerate. Okay? But all runners, or all 100-meter runners, generally have a graph that would have this shape. Where it is going to be changed.
Would it not be constant? Isn't that a little weird?
Yeah, right here it's not constant. You're absolutely right. Their rate of acceleration right here is not constant, and that's because when you first come out of the blocks, your acceleration is different because you're not upright yet. Okay, so when you're in the blocks and you come out of the blocks, you are like all your weight is coming forward to get you going. And if you've ever watched somebody in slow motion, okay, they're usually lower to the ground and their steps are a little bit to the side as they pick up speed and then they get into their full-on run. Okay, that would be, so this part here would be the smooth, I'm totally upright acceleration. This would be, I can't run any faster. Okay, and then this is, whew, I passed the finish line and now I get to quit.
How many strides would the guy have to take to run that?
It's, I can't remember the exact number, but it's like 33 or 34 strides for Usain Bolt to run the 100 meters. I mean, the guy's 6'8".
No, but for like the 1 second, 17.
Oh, God, I don't know. He covers a lot because he's a freakish athlete. Okay, like there's been nothing like him before. Okay, so yeah, when he is running at full tilt, that might be 3 steps. Might be. Okay, yeah, it is. Yeah, if you ever watch him in slow motion, it's like art. Okay, like there's just something incredibly like pleasing to the brain about watching something that's just moving exactly like it should. Okay, he's incredibly efficient. Okay, yeah, and actually that was his downfall in his early career. His acceleration was, well, it never was good. Usain Bolt is a terrible starter. If you've ever watched any of his races, he's the last guy out of the blocks. He's in last place for like the first 15 meters, and then he slowly reels everybody in until he's like 10 meters in front of them all, right? Like you can, if you ever get a chance, watch any of his races, and you can see the look on people's faces as they race against him. They're all like this.
I think we should do it
Okay,
right now.
I don't have one, I'm not gonna go searching. Okay, like every you can tell everybody's listening for his footsteps, because they know he's always getting faster and faster. So his graph is not as steep as this. Okay, his graph would be more like that. Okay, getting to the finish line. He runs at his top speed for only about the last 25, maybe 30 meters of the race. The problem is for other people, his top speed is ridiculous. Okay, everybody else gets a great start and they're up to their top speed in 25 meters, and then it's all over. They can't run any faster, and they got to hold that for 75 meters. Where Usain Bolt just accelerates and accelerates and accelerates. It's why he's actually a better 200-meter runner. Okay, he can accelerate like that and then hold 17 meters per second for 125 meters. Like nobody can catch that guy in the 200. Okay, so is that shape making sense? Okay, that's just us again being able to look at a graph and analyze and understand what that graph is telling us. Okay, so on this graph right here, this velocity versus time graph, what's this object doing?
Staying at a constant rate of 5 meters per second.
Moving at a constant rate of 5 meters per second. Okay, so it's not accelerating. This is traveling at a constant velocity, which is why the slope of the line is 0. Right? Okay. Calculate the displacement of this runner over the 10 seconds. 50. Okay, we know they're running at a constant velocity of 5 meters per second for 10 seconds, right? D equals 5 times 10 seconds, 50 seconds. Okay, everybody all right with that? All right, what's this object doing? It's increasing its what? Speed, velocity, okay? At a constant rate. At what rate? Okay, remember on this graph, the slope is telling us how many meters per second the velocity is increasing by. Okay? In this case, 2.96 meters per second every second. Right? So every second it's going just under 3 meters per second faster than the second before. Okay. All right. Calculate the displacement of this object. over 10 seconds. And you can assume that it starts at 0. Okay? I would say so. Okay, how'd you do that?
30 times 10 divided by 2.
30 times 10 divided by 2, right? You found the area of this triangle. Okay? Took the base, 10 seconds, multiplied it by the height, 30 over 2. Okay? Here's our average velocity. Here's our time. Average velocity times time equals displacement. Questions on that one? Okay. I want you to do a couple of things on this one. Okay? Okay, questions 1 and 2 require you to use the equation of the line. Okay, so the equation of the line here, y equals 3.3x plus 4.14. Okay, so 1 and 2 require you to use that. Question number 3 does not. Okay, although you actually do need some of the numbers from the equation for number 3. You're just not going to manipulate the equation for number 3. Okay, I'll give you a few minutes on that, and then we'll go through it together. Okay, so that's what we're looking at, 76.74. So we've got our 3.3 is the slope times 22 seconds plus the y-intercept, 76.74 meters per second. Okay, everybody all right with that? Okay, then for number 2, they're asking how long something will take. Well, how long something will take is time. Which axis is time on? The x-axis. So I'm solving for an x value. That means I have to take y equals m times x plus b and solve for x. So I'm going to subtract b from both sides, and then I'm going to divide both sides by m. Right? They told me that the y is 65 meters per second. So 65 minus 4.14, my y-intercept, or b, and then divide that by m, which was 3.3. So 65 minus 4.14 divided by 3.3. Okay, so it's going to take 18.4 seconds for that to happen. Okay, questions on that one? Is that the same thing we did the first day we learned how to make graphs? It is. It's just using y equals mx plus b. You use y equals mx plus b for any linear graph. What it calculates is always different, but how you manipulate and use it is always the same. Okay. All right, for the last one, calculating the total displacement. Okay. If I want to calculate the total displacement, I need the average velocity times the time. And on this graph, that's going to look like these two shapes. Everybody all right with that? Okay, now how many of you figured out what the height of this triangle was by estimating what y is right here? Okay, should we ever estimate? Not unless we're specifically told estimate. Okay, we should never estimate. Can I calculate what y is at 10 seconds? Definitely, because I have an equation that tells me how to calculate y at any given time. Okay, so I'm going to take 3.3 times 10, so that'll be 33, plus 4.14, that'll be 37.14. Okay, so I know the y value right there. Now I can calculate the area of both the triangle and the rectangle, right? So for the rectangle here, the height of the rectangle is 4.14. And the base of the triangle is 10 seconds. That's my average velocity times my time. Okay, so we're going to get 41.4 meters for the bottom. And then to do the top, okay, I just want the height of the triangle. Okay, the height of the triangle is not 37.14. The height of the triangle is 33. Okay, because the triangle only goes from 4.14 to 37.14. That's 33. Okay, everybody follow me on that one? That's a trick that sometimes people get caught on because they're like, oh, I calculated the height of the triangle. No, you didn't. Okay, the triangle doesn't go all the way down to the bottom. Okay, so 33, and this is 10 seconds, so that's going to be 333. Okay, 333 plus 41.4 should be 374.4. Is that right? I think I shouldn't do math in my head. How many times have I said that?
A lot, like.
I've been right though a number of times, but I shouldn't do it all the time. Oh, it's the y-intercept. I got it from my equation, right? It says the line goes through the y-axis here, so that's the height of the rectangle. Okay, Evan?
Could you also use the final position and subtract the original position?
Except I don't have position on this graph.
Don't, you have the numbers on the sides.
But it's not position, it's velocity.
Oh, okay.
I could use that if it was a position versus, but I would never find the error. On a position time graph, I just subtract the two and I'd be done. And I think that's what you were thinking, right? Yeah, except it's not a position time graph. And that's the danger, right? Like, we don't want to memorize, well, I do it this way on this graph, I do it this way on this graph, because what I find is people get it confused instead of, okay, this is this kind of graph, how can I get what I'm looking for?
Where do you get that extra 3 on the 333?
From my imagination. It's supposed to be 330. Yeah, you're absolutely right. See, this is why I shouldn't do math in my head. I'm good about 50% of the time. Okay. Unfortunately, that 50% is after I've made a mistake, and then I depend on the mistake to do the math right. And so yeah, it's definitely not the right answer. So 330, so we're looking at, 371.4. And then I go right back to doing it in my head. So yeah.
Can't you divide the 330 by 2?
Can I start over? Can I just go back to bed? Can I just go back to bed and start this day over? It's a good thing you guys are so sharp. Yes, I should, Hersey, absolutely. Okay, so 330 divided, you know what? I've learned my lesson. 330 divided by 2. Okay, 165 plus 41.4. That's the right answer. Right there, that one, 206.4. Let's say that on Monday we'll try this again, and I will try not to screw up as much.
Where'd you get like the 4.14 times 10?
Okay, so the 4.14 is the height of this little rectangle here, and I got it because I know this line intersects the y-axis at 4.14 because it's my y-intercept.
Oh,
Okay, and then the base of the rectangle is 10 seconds, so that's where I got the 10 from.
You should get your, you should like calculate like words, but you don't always go in the smart board, but whatever the easiest to calculate.
But I like my smartboard calculator.
But it seems like you don't.
I just try and go fast. See, my problem is I want to get this done and I want to get it done fast instead of I want to do a good job. Trust me, this is like a major stumbling point in my whole life. That's why I'm no good at construction. I just want to get this done, and then I realize it's not square or it's not right at all. 3 boards and a wall are different lengths. Yeah.
I think you need a calculator.
I have a phone. It has a calculator on it.
It's not as close as calculator.
No, when I was a kid, that was like high tech, man. Yeah, having that calculator watch. Yeah. All right. So does that make sense to everybody? How that works? Okay. What do we got? 9:28. All right. We'll call it there, and we'll continue working on. Actually, we got a lab on Monday. Okay, so we're going to be running the carts down the atrium and marking their positions, and yeah, then we'll make some graphs.